Hi, welcome to Agastya Software Technologies Theory of Computation courses. In this course, already we covered the prerequisites in part 1 and part 2, the essential knowledge, the foundation required to understand clearly so that those who want to appear the GATE examination, so they need to have a proper fundamental knowledge, which is in terms of sets, functions, graphs, relations. All these topics we covered in the earlier sessions. Now we are entering into a theory of computation. We are starting with the finite state missions. So what is a finite automata? The term automata is derived from a Greek word which means self-acting. Now is the automaton. The automaton is the plural word for automata. Automata is a singular word, then automaton is the plural. What is automaton? This automaton is the mission which recognizes patterns. This finite state mission or finite automata, it is an abstract mission with a limited memory. Why it is having limited memory, we will elaborate, but it is a very limited memory. This memory, the finite state mission, is using the finite states. Finite states are used as a memory, as a limited memory, because number of states are finite. Before we elaborate more on this one, so just to understand, the finite state mission is an abstract mission, which is not a physical mission, with a limited memory. Now in this triangle, we can see on one side a regular expression, finite automata or finite state mission. Another one is the regular language. So we can see here each can describe others. What does it mean? All these three having the same expressive power. They are the one and the same, but different ways of representing. Same expressive power. What does it mean? If you have a regular language, if you have a regular expression, then we can convert that one into finite state mission. If you have a finite state mission, you can convert into a regular expression. In the same way, if you have a regular language, then you have a corresponding FSM. If you have a FSM, you have a corresponding regular language. Then if you have a regular language, then you have a corresponding regular expression. If you have a regular expression, you have a corresponding regular language. So this is what the meaning of. All these are one and the same, have the same expressive power, different ways of representing. So we can we can convert from one to another. Now we can see the how we can define finite automata, the finite state mission. It is similar to a compiler. When we take a compiler, when you take the programming language Java has a compiler which is noted as Java-C, and we can say a Pascal, and we can see a Pascal compiler. What the compiler does, it recognizes legal programs in that language. When you write a program in Java, first it's going to be compiled. Then if it is compiled, it means it is a legal program written in Java. If the Pascal compiler, it recognizes the legal programs written in Pascal. In the same way, finite state mission recognizes legal strings. So when we design a finite state mission, for example, if you want to design a finite state mission to recognize, to identify legal identifiers in Pascal. So what is the legal identifier in Pascal? Is it need to start with a letter followed by letter or a digit. So these are the legal identifiers in Pascal. So to recognize this pattern, so this is a sample FSM. It is a start state. If any letter is encountered, it enters into the state. Then on the letter and digit, it loops through. So this is a simple FSM to recognize the identifiers in the Pascal. The FSM, now we can see an FSM has three components. One is the input tape. You can see this is the input tape. The input string always is embedded between these two symbols. This is the start of the input. This is the end. When it is reaching this symbol, which is a dollar, then it means the input string is finished. And this is the input string, and this is the read head. This is the second one, and read only head. And this is the control unit. When we discussed, FSM is a abstract machine with a limited memory. Because of it is having a limited memory and its computing capability is also limited. The computing capability of FSM is very limited because of is having limited memory. Then how this memory is built? Now you can see the third component, finite control. These are the states 0 to n. So it's having n plus 1 states and is a limited number of states, finite number of states, and it uses its states to remember the patterns or to remember. So the memory is nothing but is the states. It's not going to have any external memory. So it is not having any external memory. So the memory is nothing but in the form of states which are finite. Then that is the reason finite state machine is having a limited memory. That is the reason it is having a limited computing capability. So limited memory, limited computing capability. These two are worthwhile to remember. Now we can see how these strings are processed. When we see the previous diagram, it starts from the starting. It reads one symbol from the input string at a time. The input head moves forward direction until it reaches the dollar. Whenever it is reading a symbol, the state is going to be transitioned from the current state to a new state. Means now the control is in current state S1. When the input is reached B, it moves to another state S2. Like that, it is the finite control is moving its states. Then the head is moving towards forward direction. When the dollar is reached, then the finite state is going to end up in some state. Now we can see this is the input string we given. In this input string is given to finite automaton is a plural, automata is a singular, or finite state machine. Whenever we are giving a string to a finite state machine, what is the output? Really we don't get output. What is the meaning of output means? We can say that string which we given to the state automaton or finite state machine, we can say is it accepted or rejected. That's what we can conclude. That's what the meaning of output is. It's not the real output. So we don't get any output. After the string is given, we can say this string is recognized, means accepted. It is not recognized, means rejected. Now we can see this one, how we are going to represent the finite state machine by using a digraph, a directed graph. In the digraph, the finite control states are nodes. You can see here. So whatever in the previous diagram, when if you remember, then the input tape, then we have a finite control and a head. So the finite control, the states are in the finite control, the input string is in this input tape, and this is the read head. These finite control states are represented as nodes or vertices here. The nodes are vertices. And again, an arc, you can see a direct edge between two nodes. So the two nodes Q0 and Q1, there is a directed edge labeled with A. What does it mean? If the current state is Q0 in the finite control and the input is A, okay, upon reading the input A from the state Q0, if the finite control moves to Q1, then we are going to represent that transition in the form of a diagram Q0, Q1 labeled with A. And again, before start reading the input, the finite control stays in one state, that is called initial state. For the initial state, the notation is incoming edge. Now, after that, now we are going to represent the final states with the two double circles. Now, previously we discussed at the end of string is reached, the finite state machine ends in the final state, then the input is accepted. If it ends in the non-final state, it is rejected. Now we can see an example here. This is the input tape, this is the dollar, and these are the marks. Now we are going to read the inputs. Initial state is the Q0. In the Q0, this is now we can see the finite control here. If the finite control starts with the Q0, by reading A, it moves to Q1. Now it is moving to Q1. Now Q1 is the current state, and the current input is the B. From Q0 and B, it moves to Q2. From Q0 and B, it moves to Q2. From Q2 to A, it moves to Q5. So from Q0 A, it moves to Q1. Q1B, it moves to Q2. And Q2B, this is here. Q2B, it moves to Q3. From Q3A, it moves to Q4. Means whenever the input string dollar is reached, is Q3. Now, whenever the dollar is reached, this is the end of the input, means the dollar. When dollar is reached, when it's starting Q0 on A, it is moving into Q1 on A. From Q1 on B, it is moving into Q2. Q2 on again B, it moving into Q3. Q3 on A, it is moving into Q4. So whenever the end of input is reached, then the finite control is in the final state. Then this string is accepted, A, B, B, A. This string is accepted by this machine. Now we can see the rejection scenario. Now we can say A, B, A. Now Q0 on A, it moves to Q1. Q1 on B, it moves to Q2. Q2 on A, it moves to Q5, which is a non-final state. Is nothing but rejected. Now we can see on A, it moves to Q1. On B, it moves to Q2. On A, it moves to Q5. Then the input end is reached. Now it is end up in non-final state. Means whenever now we can make the input is finished, it is rejected. Now another scenario. This is the finite state machine M2, and now this is the input. Now Q0 on A is Q0, Q naught on A is Q naught, and the Q naught on B, it moves to Q1, which is the final state. Means whenever the end of input is reached, it end up in the final state, means this input string is accepted by this mission. Now this is the scenario Q1 and B, then which is accepted, means input is finished, it is end up in the final state. In the rejection scenario, BAB, on B it moves to Q1, on A it moves to Q2, and B it is looping. So this is one type of non-final trap state. Non-final trap state. What is the trap state? Once you entered into the state, you can't escape. That's what the trap state is. So this input BAB is a rejected input. Now we can see the transitions. On B it is reached there, on AB it is reached there, on AB it is looping over. Now input is finished. Now it is end up in the non-final trap state, which is a rejected. So now at the end what we're going to conclude is, when the input is between these two, whenever the end of input is reached in the input tape, now we can remember the input tape and the finite control, and this is the head. So it is reading until it reaches the dollar symbol. Whenever it reaches the dollar symbol, if the finite control ends up in the final state, then the input string is accepted. Whenever the dollar is reached, the finite control ends up with the non-final state, then the input string is rejected. This is what the meaning is. If the end of the input means the dollar is reached, if it is an accepting state, if it is in the final state, means accepted, otherwise rejected. This is what meaning of accepting and rejecting. Now the languages, we can see the languages accepted by finite state missions. If you have a finite state mission FSM M, then what is the language accepted or recognized by M, which is nothing but a L of M. So if there is a finite state mission, then L of M becomes a regular language. Then what is L of M is defined? L of M is nothing but all the strings accepted by M. This is nothing but L of M. So if M is a finite state mission, then L of M is a regular language. Now we can see this finite state mission M, then L of M is only one string. So this finite state mission only accepts one string, then this is the L of M. So L of M is nothing but is called a regular language. Now this is the finite state mission M. So this is, we can consider as epsilon. You can see this notation or this notation. So when we say this one, this state mission accepted epsilon AB, AB, BA. So this is the L of M. Then L of M, this is a regular language. Then this is the mission. So whenever we have a mission M, then we have a corresponding L of M, which is a regular language consisting of all the strings accepted by mission M. Now we can see this state mission M. What is L of M? L of M, you can see here, any number of A's followed by B is accepted. So any number of A's, n a power n followed by B, which is n is greater than or equal to 0, this is the language, means then what are the strings? What are the strings is, if n is 0, it becomes B, if n is 1 AB, if n is 2 AAB, and if n is 3 AAB, so on like that. This is the L of M, which can be represented in this notation. So this is a regular language. This is the corresponding finite state machine. So here we can see this is the trap state. This is a non-final trap state. So now we have to define what is the formal definition for the finite state machine. In the beginning, when we discussed input tape, this is the input tape, and these are the cells, each cell consisting of one symbol. Then the finite control is having the limited number of states and the input head. Now we can see first one is the input string over an alphabet. That is what the alphabet is. Though sigma is the input alphabet, means this string is appearing in terms of only these alphabets. If alphabet equal to 1 and 2, we can expect the string consisting of only 1 and 2. If the alphabet is A and B, then the input string is consisting of only A's or B's. And what is the Q? Q is the set of states. So the finite control is having a limited memory in terms of the states. All these states, whenever after reading the input, means the finite control moves from one state to another state. So all these limited finite number of states represented by letter Q. And this is the Greek letter delta. This is the transition function. What is the transition function? When the finite control is in one state, it means that is called current state, QC. On reading one symbol at a time, and it moves to another state, Qn. So this is the transition. So means the transition is defined delta of QC A equal to Qn. So the transitions from current state on reading one symbol, it moves to another state. Though those transitions are defined by the transition function. Then the initial state. Before reading any input, it starts with one state, that is called initial state, which we use Q0 is the notation. Then F, set of all final or accepting states. Now in this example, we can see our formal notation M. In the M, when we donate, when we using a 5 tuple, this is important, 5 tuple. In this 5 tuple, in the Q, we can denote as Q0, Q1, Q2, Q3, Q4, and Q5. This is the Q. Sigma is A and B. And the transitions we can define, and the final state is Q4 and the initial state is Q0. Only we have to define the transition. Now these are the set of states. We can see this is the input symbol sigma, and these are the set of states, and this is the initial state, which is denoted by this symbol, and this is the final states. Now we left with the transition function. So this is the transition function. So the transition function, current state, and the current input, and this is the next state. So this is defined from current state, current input, the next state. Now this is the transition function. Now we are defining if the current state is Q0, if the input is A, the next state is Q1. And if the current state is Q0, if the input is A, the next state is Q1. If the input is B, the next state is Q5. Now from Q2, If the input is B, the next state is Q3. If input is A, the next state is Q5. So all these transitions, we are going to use the transition table to represent transitions. So the transition function like that. So Q sigma Q, this is represented by the transition table. These are the states. This is the input. Q naught on A goes to Q1. Q naught on B goes to Q5. Q1 on A goes to Q5. Q1 on B goes to Q2. Q2 on A goes to Q5. Q2 on B goes to Q3. And Q3 on B, Q4, and on B, Q5. Q4 on A and B respectively, Q5 on Q5, and Q5 on A, Q5, and B, Q5. So this state, the transitions, is represented by using the transition table. Now we are going to discuss about the extended transition function delta star. What is delta star? You can see delta star defines from current state to sigma star and goes to another state. So what is a sigma star? Sigma star means we will discuss on these closures more detail in the regular expressions. For time being, is zero or more occurrence, means zero occurrence, which is nothing but empty, sigma, 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 like that. So 0 or more occurrences of sigma. More occurrences of sigma is denoted by sigma star. So the delta star means Q sigma star and is represented Q naught. What does it mean is, now we are in a state Q, on reading A, we are reaching Q1. This is, we are representing in the form of sigma. Delta, which is nothing but a Q, and sigma represents Q naught. So this transition is represented like that. Now if you have a situation on Q naught by having a string, so string on sigma is represented by sigma star. So we'll elaborate more on this one in regular expressions. For now time being, you can remember sigma is input alphabet, then sigma star is a string over this alphabet. For time being, you can remember that fashion. So sigma star we can consider as a string over sigma. Now whenever we are giving like this, on Q naught we are giving a sigma. Now we can't use delta here because this is a string. Whenever this is a string, then we have to give delta star here. Whenever you are giving delta star on Q naught, by reading of this string, and it ends up in some state. But please remember, reading string means it is not reading this whole string at a time. It reads one input from that string at a time. After the end of all reading all the inputs, it ends up in one state. That is the state. Here that's what is extended transition function. Now we can take one example in the diagram. Now we can say the blackboard. Now sigma delta Q sigma like this. Now delta star is nothing but Q sigma star. So for now sigma star you can consider as a string set of all strings. So we can consider this one set of all strings over sigma. For time being you can remember that way. Set of all strings over sigma is denoted by sigma star. So extended function delta star is nothing but, now we can do like that. So if we have one input symbol, we use delta. If it is a string, then we can use delta star. Means wherever delta is there, now this can be replaced. Instead of writing this one, can we write like that? Delta star q sigma q. This is also considered as a string over alphabet of length 1. So wherever delta is there, you can use delta star, but on wherever delta star is there, you can't use delta. Okay, so this is the very important. Extended function delta star, it can use to replace delta. So it can use to replace, so delta star can be used to replace delta. Now we are going to more elaborate again the relation between delta and delta star. Now, for example, now we're going to write a delta star. Now it end up with the q naught. Now if we're giving a string a, b, a. So whenever we are writing here, we need to remember it reads only one symbol at a time. This can be written as delta star of, from current state it reads only one input. So we're going to take one input, one state. So here we can use as a delta. So this is first, it is reading input A. So it is going to give another state. For that state, what is the input we are going to give? B, A, B. To this state, for example, if the state is Q1, then Q1, B, A, B. It becomes like that. Again, how this is going to be represented? Now delta star of, for Q1 we are giving B, for Q1 we are giving B, which is nothing but a delta and AB. Like that, this delta and delta star also. So delta star is an extended delta, means is used to apply for set of all strings over sigma. Now we can see here delta star, if you are in Q naught, giving AB goes to Q2. What does it mean? So on Q naught on A, first we are giving Q naught on A, which is nothing but a delta. You can keep like that. The remaining string is B, and you can keep the delta star as it is. Now it becomes delta star of Q naught on A, it becomes Q1 and B. Q1 and B, it goes to Q2. Like that. So if it is really confusing for you, instead of using delta, in all places you can use delta star. Now here, now delta star of Q naught. See, whenever we are giving string, you need to remember it reads only one symbol at a time. First it reads A, from Q naught it goes to another state. This becomes a state which is nothing but Q1, the remaining is BBA. Like this. From here, Q1 and B, it gives to Q2 and BA. From here, Q2 and B, it becomes Q3 and A. And Q3 and A, it goes to Q4. So we are only representing all these transitions. So at the end, the final state, after reading the whole string, it ends up with the Q4. So these are the transitions we can define. Now in the same fashion, the delta star of Q naught. So we can see delta star of Q naught A, comma, remaining input string BBAA. Now this is giving Q1. Now Q1 of delta star of BBA. B, and A. You can carry on. So, but the end of input is reached, it ends up with the in Q5. Now, this is what we are going to represent whenever we are giving delta star on state Q by giving W in the Q dash. Means after reading the whole input one at a time, that is important. Then we can represent. Then this is a walk. There is a walk or a path from Q0 to Q1 labeled by W. So this is nothing but sigma 1, sigma 2 until sigma k, if we use sigma. So which is from Q0 until Q dash. Now you can see if there is a walk from Q0 to Q5 with this label. Now you can see A, B, 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 A and A. So this is the label path. This is the walk which is denoted with the red symbol. There is a walk labeled W, which is nothing but A triple B double A is a walk labeled with this one. Now, whenever we can see the recursive function, which is nothing but epsilon. So the extended function, if we are giving a state, if the epsilon, it ends up with the same state. Now, whenever we are giving extended function Q, W followed by one input symbol. So first this one is nothing but delta star of QW, because whenever W is there we have to give delta star. So this one leads to a state. For that state you are giving only one symbol, which is sigma. Then we are giving a delta. So this is, we can say as a sigma, then we can call as a sigma. So this is what the extended function is. So delta star of Q, W and sigma, it ends up with Q dash, and Q1 with sigma ends with Q dash. So this is the recursive definition. Now the extended function Q0 and AB. When we define Q0 and AB, in the case of, you see here, now here because of one input, either we can use delta star or delta, because this is the one input. So delta star of Q0 A, first we are giving, for that we are giving B. This is also can represented by this delta star of Q0 and epsilon, which leads to Q0, A and B. So Q0 and epsilon gives to Q, Q1 A goes to Q1, Q1 and B goes to Q3. So this is the transition function, so which we can express. So simply wherever delta is there, you can replace with the delta star, but reverse is not true. Delta star means if it is a string, then you have to use delta star. If it is one input, you have to use delta. So now the languages accepted by finite state machine, L of M equal to set of all strings, W belongs to sigma star, nothing but delta star of Q0, W belongs to F. Means if there is a walk, if there is a path labeled with W from initial state to final state, set of all those type of strings is nothing but L of M. So this is the formal notation. So W belongs to sigma star such that extended function Q naught W belongs to F. If there is a labeled from Q naught to a final state labeled by W, then set of all those type of strings is L of M. And on the other hand, the rejected, then complement of M, L of M, which is denoted by like this, complement, W belongs to string such that extended function QW does not belongs to, means if there is a walk or a path from initial state to non-final state labeled with W, set off all those W's consisting of complement of L of M, non-final state. Now we can see this string. This string is accepting all the strings which are prefixing with AB. Prefix with AB followed by anything, then it is accepted, which is a final trap state. So this is the L of M. Now this one, all strings is accepted without substring 001. So without having this substring, the rest of the strings are accepted. If it is having a substring 001, then the string is rejected here. This is the non-final trap state. Now this one starts with A, any string ends with A over alphabet AB. So see, that is important. When we say sigma AB, then we can say sigma star, which is a, then we can say AB whole star. Means sigma is the input alphabet AB. Sigma star is set of all strings or input sigma. AB whole star means set of all strings over the input AB. So this is accepts set of all strings over input AB, starts and ends with A. If it starts and ends with A, accepted. On all other cases, strings are rejected. Now, so far we discussed about in general finite state machines. The finite state machines are three types: deterministic finite state machines, non-deterministic finite state machines, non-deterministic finite state machines with epsilon moves. These are the three we are going to discuss. What is the deterministic? Determined. For all input alphabets, now whenever we defined Q, sigma, transition function delta, Q naught F, all states, if you take any state which is belongs to Q, set of all states, they are going to be outgoing edges. The number of outgoing edges is equal to the number of input symbols. If the number of input symbols are 2 AB, then we need to have exactly 2 outgoing edges. Only exactly 2, not more or not less. If it is less than, like if it is 1, it is not a deterministic. If it is more than 2, it is not a deterministic. From each state belongs to Q, there exactly the outgoing edges, the number of outgoing edges is equal to the number of input symbols in the sigma. Then the finite state machine is called a deterministic finite state machine. Otherwise, it is called non-deterministic. In general, FSMs are non-deterministic. Now we can see here. Now this is the sigma star or sigma equal to 0 and 1. We can see from the state exactly 2 transitions on 0 1 transition, on 1 1 transition. From here exactly 2 transitions on 0 1 1 on 1 1 transition, on 0 1 transition. So means it is a deterministic finite state machine. Now the trap state. What is a trap state? Once it is entered into a state, then this is sigma. For all inputs belongs to sigma, it loops over, means it can't escape from the state. This is called this is called trap state. If the trap state is non-final trap state. Then if it is final, then final trap state. So the final trap state is like this. So far we discussed finite automata, DFA principles. Now it is the time to do some exercises using DFA. Before we proceed the exercises on DFA, let's recap some of the basic concepts as required, which is nothing but what is a string and what is a language. What is a string? We can see string is a character or characters. String of characters these are the fundamental blocks in computer science and engineering. We already discussed an alphabet. So a string over an alphabet varies with the application. Means the alphabet they're choosing for each application is going to be a different. So what is an alphabet? Alphabet is a non-empty finite set, and the members of an alphabet are the symbols of the alphabet. So when you define an alphabet, the members in that alphabet are nothing but the symbols of an alphabet. We use the Greek symbols sigmas so to denote alphabet. And we can see this is an alphabet with consisting of 0 and 1, and another alphabet, this is sigma 1 and sigma 2. This is another alphabet consisting of A to Z, and this alphabet is consisting of 0, 1, X, Y, Z. So alphabet is sigma alphabet set of finite number of symbols, always finite. This is very important. Always finite. Then what is a string? A string over an alphabet. This is important. What is the meaning of over an alphabet? Means the symbols in the string must consisting of those are belongs to the alphabet. So a string over an alphabet is a finite sequence of symbols from that alphabet, usually written next to another. Means like the symbols, like for example, if the alphabet is like sigma 2 ABC, then the string is BA, CC, ADD. Like we are writing the symbols of alphabet next to each other without spaces and commas. It forms a string over that alphabet. Now we can see sigma 1 equals 0, 1. Then string over this sigma 1 is 0, 1, 0, 1 is a string over sigma 1. This is very important. String over sigma 1 means the string must consisting of only symbols of sigma 1. This is very important to note. Now string over alphabet sigma 2. Now the sigma 2 consisting of A to Z. The string over sigma 2 is nothing but this is a string, means only these symbols are included in the string. Now if W is a string over an alphabet, then the length of the string is denoted by mod W, is the number of symbols that it contains. For example, if sigma equal to 0, 1, then if you have a string 101, then mod of 101 equal to a 3. And the length of the string of length 0 is nothing but is called epsilon. Then mod of epsilon is 0. Now empty string is denoted by epsilon. Then if this W is this string over the alphabet, now you can see this is over alphabet, for example ABC, the length of this one is 7, means 7 number of symbols are included. Length of epsilon is 0. If the W has a length n, and we can write W equal to W1, whereas Wi belongs to sigma. Then reverse of a string, if W equal to ABC, then reverse of W equal to CBA. Then the substring is, for example, if W equal to ABC, ABAC, then what is the substring of the W? We can take CAB is a substring, or BCA is a substring. Substring of string W, when we can say string Z is a substring of W, if Z appears consecutively within W, it need to appear not A here and B there. No, it need to appear consecutively within W. You can take BAC or CAB or ABA or BAC or AC consecutively within the W. You can take within the W, you can cut the piece somewhere, then consecutively how many symbols appear, that is called substring of W. Now like this, for example, CAD is a substring of this one. Now this is the consecutively appearing here. Now what is a language? Now we can see sigma is an alphabet, 0, 1, or this is sigma 1, the sigma 2, ABC. Then string means like string over sigma 1, string over sigma 2. Now what is a language? What is a language? So now we can see epsilon is an empty string. Then what is the empty language? Before empty language, empty string, now we can see if sigma equal to ABC, sigma power 2. What is the sigma power 2? All set of strings over sigma of length 2 is denoted by sigma power 2, nothing but AB, AA, BA, AC and CA, like that, so on, of length 2. If we see sigma power 3, set of all strings over sigma of length 3. Then sigma power k, set of all strings of length k over sigma. Now when we say a language L over sigma is a subset of sigma power star. What is sigma power star? Sigma power star equal to epsilon union sigma power 2, so on. The union of all these means, what is sigma star? Sigma star is set of all strings over sigma. Then that is called sigma star. Then language is subset of sigma star. Now we can see empty language. The difference between empty string is epsilon, and empty language is denoted by pi, like this. Empty string and empty language. And again, the language consisting of empty string is not empty language. This is also very important to note. Now the concatenation. So concatenation means if there are two strings, for example AB and XY equal to BB, then concatenation of XY, first we need to take all the symbols in the string from X, AB followed by Y. this is the concatenation. So the concatenation of two strings of x of length m and y of length n, then we can take x and y, we are going to denote like that. Concatenation. So xy concatenation is not equal to yx. It is not a symmetric. Concatenation is not symmetric. xy is not equal to yx, because in xy first the symbols of x appears followed by y. Here the y symbols appears followed by x. Then reverse of x is like this. So then this is the x and y. Then concatenation is this one, and the reverse is CAB. Now this is already we discussed. The set of all strings over an alphabet sigma is called sigma star. So sigma star is nothing but sigma power 0, which is nothing but epsilon, sigma power 0 union sigma power 1 union sigma power 2, means all strings of length 0, which is nothing but epsilon, all strings of length 1, all strings of length 2, so on. And this is sigma star clean closure. We are going to discuss about closures later in the regular expressions. Now positive closure, which is nothing but not excluding the length 0, it becomes positive closure. If we add a epsilon to the positive closure, it becomes clean closure. Now the language continues. So what is a lexicographical order of strings? It is nothing but the same order as familiar with the dictionary order. That's what lexicographical ordering. And the set of all strings over an alphabet, like this, is an infinite set of all strings over this one of any length. Now when we say string x is the prefix of string y, if the string z exists where x, y, x, z equal to y, then is called, what is a prefix? For example, this one, this becomes a prefix. ABA becomes prefix of ABA, BZ. This is the prefix. And a prefix and a proper prefix is a prefix and a proper prefix. So if we can say A is a prefix, AB is a prefix, ABA is a prefix, AB is a prefix, but it's not a proper prefix. Yes. And how many ways we can describe? We will discuss this one, enumeration. We are going to discuss about regular expressions, and we are going to discuss about context-free grammars, set notations in the upcoming sessions. Now we are going to elaborate more on how to design. Now we are coming into interesting topic of designing of finite state machines. So the first one we are starting here is, let us formally specify the DFA that accepts all and only the strings of zeros and ones. They have sequence of 0 and 1 somewhere in the string. Then this is the language we are writing. L equal to W such that W is the form of, so W is the form of X, 0 and Y, where and X and Y is consisting of zeros and ones. Means the alphabet is 0 and 1. The string is such that it is appearing any zeros and ones here, any zeros and ones here, doesn't matter. It need to have this pattern, 0 and 1 pattern somewhere in the string. So whenever it is having 0 and 1 somewhere in the string, then the DFA need to accept. So this is the language. So we have to design that DFA. Then how to design that DFA? This is important. So when we discuss that DFA, how we gonna designing? Let's recap our mission. Our mission consisting of input tape, finite control, and head. The head starts from the cent symbol until the dollar and reads one symbol at a time. Whenever the dollar is reached, then if the finite control ends up in the final state, then it is accepted. In non-final state is rejected. So the condition here is in the string somewhere 0, 1 appears, it need to be accepted, otherwise rejected. So let's start with that one. Then when we start this one, then we have to remember our DFA mission M, tuples Q, Z, delta, Q naught, and F. These are the 5 tuples. Now when we see, we are starting with the Q naught. When we are starting with the Q naught, we are scanning the input. When we are scanning the input, we are interested in this pattern, 0, 1 pattern, 0 followed by 1. Whatever prefix and suffix, it doesn't matter. This is called prefix, proper prefix. This is suffix, it doesn't matter. After seeing this pattern, then we happy to go, say accepted. Until this pattern appears, we have to scan for this pattern until this pattern appears or end of the string happens, means the dollar symbol. When our dollar symbol comes without reaching this pattern, then it is rejected. So whenever, while looking for this pattern, so while scanning one thing at a time, as we remember, finite state mission is not having any memory, any external memory. It only uses the states for remembering. This is important. It only uses state to remember the past input. This is very important. It is only uses the states to remember the past input. It's not having any states. So now whenever it is starting with the Q naught, it is trying to scan looking for the pattern. Whenever it's looking for the pattern, if any ones coming, so then it is looking for the pattern 0, 1 starts with 0. It is not interested in the ones because the pattern is not starting with 1. It just skips. Like whenever in this state, we're still searching for the pattern. Still searching for the pattern. This is the initial state. Whenever it is reaching symbol 0, so it need to remember whenever it is reading, whenever it is now this is the state Q naught. Whenever 1 is coming, the pattern is not there. Whenever it is moving, so this is the state. Still, it didn't encounter any symbols of the pattern. Whenever 1 is encountered, it doesn't know about what is coming after 0. Let's assume 1 comes, means this 0 is belongs to the pattern of 0, 1, what we are looking for. If 0 followed by 0, this is not the 0 we are looking for because this is not becomes pattern. When we know, until we move further, then only we know. Currently we have no idea of when our 0 is coming, we have no idea that this 0 is belongs to the pattern or not. After this 0, based on the coming symbol, only we can decide the previous symbol belongs to pattern or not. Now let's assume that this belongs to a pattern. Now we are remembering a state. So we have seen, now we are coming to this state by making an assumption that we have seen the first symbol of the pattern 0, 1 we are looking for. That's what we are making an assumption. We are coming here. Immediately, if we are encountering 0, what does it mean? No, previous 0 is not belongs to that pattern. Maybe the current 0 maybe belongs to that pattern. You need to be the same state, because the state is representing a memory. The state is representing a memory. This is very important. So now, like that, again 0 is coming. Now we are again making previous 0 is not belongs to pattern. Maybe this 0, the start of the pattern. Like that, we are looping on 0. Whenever 1 is coming, yes, the previous 0 of that pattern, we have seen that pattern, happy, entering into the final state, final trap state. The rest we are not interested. So this is the DFA belongs to this one. Now the transition table for this one is, now we can see, now this is the, when we say that is the DFA, we explained the design. Now, what is the transition table? The transition table Q0, Q1, Q2. Now the symbols is 0 and 1, and Q0 on 0 Q1, Q0 on 0 Q1, Q0 on 1 Q0, Q1 on 0 Q1, Q1 on 1 QF, QF on 0 QF, QF on 1 QF. This is the transition table. Now the transition delta, when we say Q0 on 1 is Q0, delta Q0 on 0 is Q1. Like that we can define delta. When we say delta star, when it comes delta star, state becomes followed by more than one symbol, is a string, then we need to use delta star. If it is one symbol, then use delta. If the string, we have to use the delta star. Delta star of Q0 0. So first Q0 on 1, Q0, and a Q0 on 0, Q1. This is Q1. Like that, this is the way we define the finite state mission. All the best, and see you guys in the upcoming session.